Welcome to The Explainer. Today, we're literally stepping into the boots of a blast furnace operations engineer to uncover the intense thermal science of transforming raw coal into high-grade metallurgical coke. We're going to look closely at exactly how a precise blend of coals, carefully manipulated heating rates, and intense carbonization can absolutely make or break the productivity of massive steelmaking operations.
Just look at the sheer scale of a modern blast furnace. As an engineer, you know this beast has a massive, non-stop appetite for the absolute perfect fuel. If you throw subpar material in there, your productivity drops, your fuel rate skyrockets, and the whole operation suffers. We have to maximize efficiency. And well, that all starts with engineering the perfect coke.
So here is our engineer's blueprint for the day. First, fueling the blast furnace, then hard versus indigenous domestic coal, the art of coal blending, inside the pilot oven, heating rates and plasticity, and finally, engineering the perfect coke.
Let's jump right into Section 1, Fueling the Blast Furnace, the non-negotiable demands of steelmaking.
We can't just dig up raw coal and chuck it straight into the furnace. It just doesn't work. It lacks the physical strength and chemical purity. An operations engineer knows that coke is actually a multitasking powerhouse. Sure, it acts as a primary fuel, but it also serves as a crucial reducing agent, meaning it strips oxygen away from the iron ore to leave behind pure metallic iron. On top of that, it literally has to physically support thousands of tons of raw materials piled high above it inside the furnace, all while providing the essential permeability that lets hot gases flow upward. It's a pretty tall order.
Moving to Section 2, Hard vs. Indigenous Domestic Coal, Sourcing the Right Ingredients.
If we pit these two against each other, the difference is night and day. On the left, you can clearly see the premium, kind of lustrous shine of the highly mature hard coal. But on the right, that's our indigenous domestic coal, duller, blocky, and super abundant. They look completely different, and trust me, they perform completely differently.
But the real story here is in the data. That expensive, premium hard coal, it's packing an impressive 86 to 97% carbon content. On the flip side, our highly abundant Indian indigenous coal carries a massive 35 to 45% ash content. That high ash is a major industrial bottleneck because more ash means more slag and wasted heat in the furnace. But because of national priorities to reduce import dependency, we absolutely have to figure out how to use it efficiently.
Which brings us to Section 3, the art of coal blending, the industrial baking process.
Since we can't rely solely on expensive imports all the time, we have to engineer a solution. We blend. Think of it exactly like a baker mixing different flours, some for gluten, some for flavor, to get the perfect dough. No single indigenous or imported coal satisfies all our extreme blast furnace requirements on its own. Blending combines the best traits to achieve optimal plasticity, lower overall ash content, and ultimately superhuman mechanical strength.
To prep this industrial dough, we crush everything down to exactly 0 to 3.2 millimeters. This is crucial for improving bulk density and ensuring uniform heating. Then, we knead in precisely 8% moisture to act as a binder, along with any necessary additives. Finally, we stamp charge it, which essentially means we mechanically compress the blend into a massive, dense, solid cake before it ever goes into the oven.
Section 4, Inside the Pilot Oven, the Crucible of Carbonization.
Obviously, we aren't going to risk a full-scale industrial oven on a brand new recipe. We need to test it first. What you're looking at here is the 20-kilogram pilot oven at RDCIS, where engineers safely replicate massive industrial thermal dynamics on a much smaller scale. Inside this sealed, completely oxygen-free pilot oven, we heat our stamp-charged coal blend starting from 750 degrees, pushing it all the way up to an intense 1100 degrees Celsius. And because there's zero oxygen, the coal doesn't burn. Instead, it carbonizes.
Tracking the thermal journey this rock goes on is honestly fascinating. Up to 250 degrees, it's just drying out. But at 300, it softens, reading right into the critical plastic stage between 350 and 550 degrees. In this very specific window, the coal literally melts, swells, and fuses together. Then, entropied volatile gases are forcefully released before the entire mass resolidifies and shrinks into a final, hard, porous coke structure right around 1100 degrees.
If you visualize what's actually happening inside the oven, notice the uncarbonized center. Flanking it are these molten plastic layers at 350 to 500 degrees. As heat transfers inward from the superheated oven walls, this plastic layer slowly creeps toward the center, while the volatile gases escape upwards, leaving behind the solid coke zone on the outside.
All right, Section 5, Heating Rates and Plasticity, the microscience of strong coke.
Here's where the real microscience kicks in. The magic isn't just in what temperature we hit, it's how fast we get there. Data from a GeoSar plastometer, which is a tool that tests fluidity, reveals something remarkable. By increasing the heating rate by just 2 degrees per minute, moving from 3 degrees to 5 degrees per minute, we actually delay the solidification temperature by up to 19 degrees. This drastically widens the plastic range of the coal blend.
So the big takeaway here? A higher heating rate blows that fluidity curve wide open. It gives those molten coal particles way more time and way more fluidity to bond tightly with each other. Better interparticle bonding directly translates to a much stronger, more resilient final coke structure.
Finally, Section 6, Engineering the Perfect Coke, Grading the Final Product.
Okay, carbonization is complete, the oven is pushed, and the red-hot coke is quenched. But our job isn't over. This is our final product, and an engineer doesn't just guess. They grade it against strict, non-negotiable blast furnace metrics. We are looking for uniform sizing right in that sweet spot of 20 to 80 millimeters to ensure good gas circulation. We need low moisture, high fixed carbon for heat, and critically, we need that ash content to be as low as humanly possible, ideally below 12.5%, so we don't choke the furnace with slag.
Now for the really heavy-duty metrics. First up is the Coke Reactivity Index, or CRI. This measures how fast the coke reacts with furnace gases. We need a CRI of under 30%, period. If it's higher, it reacts with carbon dioxide way too fast and degrades prematurely in the upper, cooler parts of the furnace, rather than surviving down to the bottom where we really need it to do its job.
On the flip side, we have CSR, or coke strength after reaction. After it's been exposed to those intense, high-temperature gases, how strong is it physically? We demand a CSR greater than 60%. This ensures our baked product doesn't just crumble and get crushed into powder under the sheer weight of thousands of tons of iron ore piled above it.
This right here is our ultimate optimization blueprint, keeping moisture under 1%, volatile matter under 1%, CRI below 30%, and CSR above 60%. When we hit these exact marks using smartly blended domestic and imported coals, we guarantee lower fuel rates, far fewer bottlenecks, and we absolutely skyrocket our blast furnace productivity.
We've seen just how perfectly we can engineer this intensive thermal process to turn even challenging indigenous coals into a structural and chemical powerhouse. But it leaves us with a pretty fascinating thought to consider. As the entire world pushes hard toward a green steel future, how will this incredible, highly carbon-dependent science adapt? What on earth replaces the perfect metallurgical coke? It's something every operations engineer is thinking about. Thanks for joining me on this explainer, and keep questioning how the materials around us are engineered.